Sure. Well, we're the FOX2 Maximum PowerPoint Tracking Senior Design Group at RIT. So I'm Brent Salmi. Okay.
I'm Ian McKenzie.
I'm Bryce Salmi.
I'm Dan Corriero.
We're all senior electrical engineering students. As you guys already know, we're the FOX2 Maximum PowerPoint Tracking Maximum PowerPoint Tracker Senior Design Group, and we are going to be overviewing the results of our project, and everything looks really good. So we're going to show you the document that we put together for full unit testing, and it is pretty long. We're going to breeze through it. We'll paraphrase a lot of the discussion, and we'll look mostly at the charts, the diagrams, the results, and it's available on the Edge website for viewing later. But we will start by going into the test setup that we used to actually test our unit. And just to backtrack here, this is the final result of senior design, and it is a 2-channel maximum PowerPoint tracker for FOX2, and everything works. It fit inside the specifications. It survived thermal chamber. It gives us maximum power, and we'll go into how it does that and why in all of our analysis. So I'd like to start off first with just a quick explanation of our test setup that we used. It was a very basic setup, and one that was recommended by AMSAT. Since we don't have a solar panel simulator to simulate the actual solar panel, we had to sort of make do with what we could find. This is a simple diagram. Excuse me. Simple diagram of our solar panel model and our test setup. So we used a variable voltage supply and a series resistance to model the solar panel, and at different temperature ranges. And we can do that because the solar panel exhibits an effective series resistance based off of irradiance levels and temperatures. As the panel gets colder, our output power actually goes up slightly. And obviously, as irradiance increases, our output power increases. So that was directly attached to the solar panel inputs of our maximum PowerPoint tracker, which was then connected to our electronic load, which served as the load that we were powering, and we could manually or computer through the computer change how much output current we wanted to provide the load. And a computer running Python software was also used to talk to both the electronic load and the maximum PowerPoint tracker and get data from that. And it simulated the internal housekeeping unit on the satellite. So we modeled the internal housekeeping unit's request for data, and so we received data packets with all of our telemetry that's expected from us. So we'll continue on here. So I'd first like to just overview quickly. These are measurements derived from our efficiency testing, and the reason that we did that was that when we tested our maximum PowerPoint efficiency, we had input and output data, so input and output voltages and currents, which you can get a lot of data from. So this is at a simulated 28 degrees C solar panel temperature. Everything was set up for 28 degrees C. Our resistive temperature detector, the temperature measurement was set up for 28 degrees C. The solar panel simulation was set up for 28 degrees C. So everything was at that temperature setting, and the x-axis is output current of our MPPT, and the y-axis is voltage in watts, respective to their plotting data there. The red line is the solar panel voltage. The purple line is the maximum PowerPoint tracker output voltage, and the blue and green line are input power and output power, respectively. So I like to mention that as we increase output current, you'll notice that the output power rose linearly, and our solar panel voltage decreased during that time, and that's because we had more power available than was requested from the load, and that would be signifying that the batteries on the FOX2 satellite are fully charged, and we don't need as much power as available from the from the actual solar panels. So we're actually in an output voltage limiting condition, so we're protecting the load from overvoltage. Once we reach about 1.4 amps, excuse me, on the output, we actually we start to provide maximum power, and we make sure that we are regulating the maximum power so that regardless of the output load, so regardless of the satellite's output current and in other conditions, we provide as much power as possible. That is maximum power point tracking. And as you can see, our output power rose, and then our input power remained constant. Our output power also remains constant. As you increase output current, you get a little bit more loss in your output, in your DC to DC converter as you increase current a little bit. So that's why it dipped down just a little bit, but it remained maximized. And the output voltage started to decrease a little bit, as expected. And
to conserve energy. To
conserve energy, you can't have more power than power in is power out, and considering efficiency as well. It's also good to note that the solar panel voltage also, once we reached max power point, the solar panel voltage became regulated, and we regulated that input voltage to our maximum power point voltage that we were reading from the temperature. And you can see that the voltage stayed constant as we increased the output current. So that is essentially exactly what we wanted to see for our maximum power point testing. I will go to the next graph, and this is a graph showing output power based on the temperature setting. So the solar panel was simulated at 28 degrees C, but the RTD temperature setting on our maximum power point tracker was misaligned. It was set to negative 60 degrees C, then it was aligned at 28 degrees C, and then put to positive 60 C. So it was reading an inaccurate state. And as you can see, the blue line is the correctly matched 28 degrees C. We maximize power from our solar panel when we are tracking temperature correctly. If we aren't tracking temperature correctly, we're not actually operating at the max power point. And you can see, because although during the output limiting case, when we're not requesting more power than is available, all three cases align just as expected. But once we need maximum power, only the correctly matched maximum power point condition gives you that. And our entire methodology of tracking max power point is based off temperature, and we've achieved that. So that this graph helps to show that. Excuse me. And just quickly, this is outdoor solar panel testing. We grabbed a solar panel from a friend. It was not tuned for our circuit, but we just showed relative data. I won't go over this too much for time reasons, but we had a supercapacitor load in parallel with the actual electronic load, and that provided a simulated battery where it would act as a battery where it was discharged. And when we requested a lot more power than the maximum power point tracker could handle, so we were outputting maybe 3 or 4 watts with this panel. We wanted 5 or 6. The batteries started to discharge, but the maximum power point tracker provided constant maximum power it could. So that was a test that AMSAT wanted us to try, and it looks like it worked out very well for us.
So basically, no matter how much power we ask for it, it will stop the solar panel voltage at the max power point and continue to provide max power. But the output voltage will drop with the batteries.
So if our maximum power point tracker was not working, and you requested additional output current, your power would start to decrease, and that's exactly why we need our circuit in line between the solar panels and the load. I invite you guys to read the rest of the document. It explains in more detail what's going on. So, do you want?
Yeah. So I'll quickly state that there was actually an error in the specifications. So back in December, when we agreed upon the specifications with AMSAT, we all agreed upon 7.24 watts. Now that is the maximum power available from the solar panels at 28 degrees Celsius. We actually neglected the fact that at negative 60 you get maximum power, and that turns out to be just under 9 watts. This was actually missed by everyone, including AMSAT. Everyone kind of completely missed it. We just realized it when I was writing the technical document. So I contacted AMSAT, and we worked it out that the board will be tested to the just over 9 watts, but the specification remains at 7.24 because that's what was agreed upon. There's actually no worries for the circuit. We've put like well over 10 watts into it, and it's completely fine. But yeah, so that was actually a lesson learned in solar panel operation. So here we just wanted to test that the 7.24 watts was the maximum power. We went and we tested it at 9.122 watts,
just above it.
Just above it, and that proved the test that AMSAT would perform due to the increased power, and we performed fine. Actually, yeah, we put almost 10 watts in, actually 9.7. So that was
for
the actual measured value. Yeah, that was for 10 minutes. So
yep.
So no worries on that. And if anything does come up, maybe do the NASTA-G rating on that. The circuit's very scalable. You just switch out the part. No configuration changes. So, yep.
Okay.
Okay. So so the MPPT was rated for a maximum input voltage of 22 volts. Pretty simple test to test that would work at that and just a little bit above. Basically, just connecting the AMSAT electronic load just to pull about 200 milliamps as the minimum load, and basically just kind of increasing the voltage and verifying that the circuit was still operating as expected. We push it just a little above to about 23.5 volts, and everything measured and checked out as expected.
It should be noted that the only real concern for input voltage is the input capacitance, which is rated to 50 volts on our board, and the MOSFET gate is also a concern, but our circuit has a MOSFET driver that we built discretely where we can level shift that voltage. So if the voltage is increased, we can scale appropriately our MOSFET driver, and we will meet all specifications. There's really the input voltage limit is set by what components you pick for the circuit. There's no design change. So we've met that specification.
Okay, and then next up was the output voltage limiting. Just as a reminder, we're not regulating the output voltage, but limiting it to 4.1 volts. Basically, we wanted to make sure that it was limiting at 4.1 volts over all operations, all operating conditions. We used the data from the efficiency test results to verify this. So basically, going through each temperature and verifying that the output voltage never went above the 4.1 volt maximum. In fact, for the most part, it stayed around 3.9 volt, 3.9 to just about 4 volts. It worked as expected, and just as a reminder, we're only ever we're only limiting or need to actually limit to 4.1 volts when there's more power available from the solar panel than the load is requesting. Additionally,
yeah, that pretty much sums it up.
Yeah.
So yeah, it should also be noted that that we did limit to about 3.9 volts in all cases, and that's simply due to resistor tolerances on our sampling. We could play around with the output voltage limit circuit and get that closer to 4.1 if needed. It can be scaled any which way we want, but we did.
Just a moment, can you go back?
Sure.
To the table?
Go for it.
So the upper two show the data for a certain value of the irradiance. Temperature is 60 or minus 60 in the top?
All of them. So the top one is negative 60.
No, top one 60.
60.
Oh, sorry, 60. Yeah. Then we have then we have 28 and then negative 60. All of that's at 135.3 milliwatts.
That's a very rough
That's-
calculation on our
yeah.
part because the
That's-
series resistance model. It's hard to say
Yeah.
what radiance,
That
but
is
that's
AM0 from some Spectral Lab solar cells. That's
Okay,
space.
So the upper three
Radiance.
are correlated to the irradiance. You have the change in temperature.
well, they're all correlated to an irradiance. Basically, it's more or less settings of the RTD. So we set it to 60, 28, and negative 60, and we essentially change the series resistance of our model to scale appropriately with that. The reason I put irradiance in there was because although we can't hit an accurate figure, we can get in the ballpark of at at this irradiance will have about this much power available. That's due to our model. We don't have a solar panel simulator. But what that basically does is it says that that we're receiving maximum power. We're receiving a high amount of power. Whereas the last chart shows you at a lower radiance, 34 milliwatts per square centimeter, which basically says we don't have maximum power available. So our max power we ever achieved in this case was 1.6 watts output because of the lower radiance, and that was set at 20 degrees C.
And even then, the circuit was working fine and still protected the load, because the load was at minimum load, so we still had more power coming in. So yeah.
Does that answer your question? So next we'll go into the resistive temperature detector maximum power point voltage tracking accuracy. Our entire methodology for maximum power point tracking relies upon the temperature of the panel, and as long as we track the temperature of the panel and we know the exact panel we're using, we can estimate the maximum power point voltage. And if we regulate that solar panel voltage correctly, then we achieve maximum power. So going to this is a quick chart that I did early on into the design, where it just relates temperature in Celsius to various parameters, our RTD resistance, our maximum, our solar panel voltage. Then we can feel free to look at that in more detail. Excuse me. This is the results of the test. Basically, I powered on the maximum power point tracker and varied the RTD with minimum load. We weren't looking at the output power at all. We just wanted to power the circuit, and we measured over a varying resistance of the RTD, which was set using a potentiometer for testing purposes. We measured the actual RTD voltage that we get out from our matching circuit that we've created, and it matched very well. The blue line is the simulated ideal output voltage curve that we get as resistance is increased. Now this is basically going from negative 60 C to positive 60 C from left to right. And the dotted red line is what we actually measured, and we have no more than 1.2% error in that circuit, so we were pretty happy with that.
Yeah. And it is noted that the RTD response is actually inverted from here, so this is the inversion and scaling to produce the predicted voltage. So this is that voltage that predicts the max power point.
From our DDR, quickly it was explained that the temperature coefficients of the RTD are opposite of that of the solar panel. So as temperature increases, the solar panel voltage drops, but the RTD voltage increases. So we have to scale it and flip it and match it. So next we'll go into efficiency.
Efficiency was another big engineering spec that we had to meet. Initially our spec was set at about 90%. Due to the complexity of the circuit, getting up to efficiency levels that usually require synchronous buck converters, which are very complicated circuits. Due to the timeline of MSD and what was available, that was kind of hard to do, so we actually stuck with a non-synchronous buck converter. And we talked with AMSAT about this, and we actually were shooting for about 80% efficiency.
And MSAT was fine with it. They wanted us to focus on the actual algorithm.
So, I mean, shooting for about 80%, kind of showed it was a proof of concept of the MPPT versus optimization.
Going through the power loss throughout the whole board, if we were to go to synchronous drive of the buck converter, and we were to reduce the power loss in the we have linear regulators that convert the solar panel voltage into voltage that the op amps that run the MPPT can operate on. If we were to switch those to a switching or whatnot, we would easily get up to 90%. We could get very close. So we know we've identified the direction that is to be implemented in the final design to achieve 90%. But because of complexity of the project, we wanted to focus on getting our methodology to work.
We would like to stress again that MSAT was completely fine with the 80%.
So I'll go through here.
So essentially we did efficiency testing at different temperatures. We had the test set up for 60C, 28C, minus 60C. The RTD settings were set for those temperatures respectively, and the test was carried out. Essentially we we looked at V in, I in, output voltage and current out, and to get an efficiency plot versus varying loads. You can see here we varied the output current and got this efficiency curve. All the tests, I think except one, were held at the constant irradiance of 135.3. But here, what was this? 82.317, so well within our modified spec that we talked about with AMSAT. And we went on to testing 28C. Essentially the same thing, set the test setup for 28C, varied the current, and we maxed out at about 81.1% efficient. So, and then we did another efficiency test at 28C, but we kind of wanted to show what the efficiency would look like at lower power levels, i.e. Lower irradiance levels, and you could see that 68.4%, which was expected. That was at a very low output current. So. And again, minus 60C. When we built this project, we knew that we were going to be varying from minus 60C to plus. So
I'll add on to that. The panels experience a negative 60 to plus 60 degrees Celsius temperature swing, while the electronics inside are within the specs that we had.
And we'll go into that.
So we had to design for the higher temperature range. Yeah.
So next was MPPT response time. Do you want to take that?
So the response time is actually the DC converter turning on, and that was actually largely governed by the soft start circuit that we implemented to control the startup of the pulse width modulator. And if you want to go to the next slide. So our spec was 100 milliseconds. So as the satellite tumbles around its axis as it's orbiting, the panels will be going in and out of sunlight. So you don't want to spend too much time not producing power because you only have a couple minutes or a couple seconds. So we aimed to slowly start up the RTD, sorry, not the RTD, the PWM to limit the current that rushes in, but also I guess keep it quick. So we were able to measure that the input and output voltage started, I think, well under 30 milliseconds.
So basically, we have our response times for the input voltage to be regular. The maximum power point tracker was the solar panel simulation circuit went from off to an on state, and all of the load and the MPPT were set up to go right into max power point tracking, and we I'll go to a graph right here, and we measured the time that it took the MPPT to reach that voltage. So for instance, right here, this is the solar panel voltage. So there's 0 volts in the solar panel.
This is VO. This is VO.
Oh,
it's solar panel.
Yep.
And VO.
So, and you can see that right when we turn it on, the input capacitance and the MPPT is starting up, and then we regulate right to maximum power point voltage, which for this was just about 16.4 volts, and the output voltage was also the rise time of that was also measured, so that we could see the total system response. That how long did it take for us to get output power to the load, and the longest time that it took was 20 milliseconds, and that's basically our soft start circuit. So we can adjust that manually as needed. Should be noted that these little spikes here are actually part of the power supply used to power to simulate the solar panel. We see those same little startup spikes from just attaching the electronic load to the power supply directly and turning it on.
Actually, those are noticed when we were bringing up the AMSAT active load.
Yep. So basically, we go through different temperature regions as well. I'll let you.
Yeah, I think we should move on from here. But oh yeah, I guess that's the same. Did you go backwards or forward?
No, forward. So this is the output voltage limit startup time. So when we were not at max power point. It's the same test, except we measured the rise time for the output voltage to be limited. So we were not in max power point regulation when we started up, and the maximum time that we saw was 30 milliseconds to start up. So well within 100 milliseconds spec. So again, all of these are artifacts of the actual power supply. take this.
So we actually got a chance to go into the environmental test chamber down in the CAST SMD lab, and so that was nice to spend some time and to characterize this circuit based on its temperature response. And what we did is we held the RTD settings at 28 degrees Celsius, so as if the solar panels are 28 degrees Celsius, and we varied the panel. Not the panel. We varied the max power point tracker temperature because we were trying to isolate what changes did the circuit induce onto the tracking due to temperature.
So
as opposed to the changes on the solar panel.
The actual RTD was brought outside of the test chamber and kept
And
in outside.
it was a
temperature.
potentiometer, and So here are some of the plotted results. So right here is actually the MSP 430's report of temperature, and you can see that we started at 28 degrees Celsius, went up to about 85 degrees Celsius, and then dropped down to -40. These are all relative. These aren't scaled. I do want to note that there's no calibration on here. One of the specifications in the I2C reporting to the IHU is that we don't perform any calibration. That's done on the ground. We report.
We send raw bit values. We've scaled appropriately, but it's not a calibrated sense at this point.
Yeah. And also the MSP 430 was on the board, so any variations in its ADC could be present as well. So, but even with that, you can see that the output current, which was kept constant, varied slightly with temperature. As expected, it actually, I think, didn't go more than about 30. Is that, yeah, it's going 30. I think 30 or 40 milliamps.
25 million.
25. The specs on the next page, but and that has a positive temperature coefficient. The solar panel voltages actually kind of as somewhat expected. That circuit has a negative temperature coefficient, and those actually stayed within about 20 or 30 millivolts, which is actually pretty good. So in the next page, we'll show the data. Oh, sorry. Now this is actually the same test, but performed from -40 up to 80, 5 degrees Celsius as the temperature reported. And this is with output limiting. So this is in a state where we have a lot more power coming in than we're using. So if you want to go to the next slide, so you can see that over all the ranges here. Oh, this is the
This is the measured
change?
data.
Is this that change?
No, there's no. I never put the change.
Oh, sorry. Yeah, that's the. This is the minimum load right here, or just above minimum load, and for the output limiting case, and the 1.585 amps is the case where we're regulating, and those are actually measured not with the MS530, but with outside external voltmeters and current meters.
The output current remains
Constant.
0.585.
Yes.
Yeah,
And actually it only varied by 30.
The electronic load is a constant current load.
Yeah.
So no matter what the circuit did, it always pulled 1.585
Yep.
amps. So even if the output voltage is changing, it's always pulling that. Yep. It should be noted that that in the text.
What we were looking at was the current sense and making sure that's how we got that to show. So if we move on.
Just an FYI here. The maximum shift in power output that we saw was 20 milliwatts over the entire range, which is pretty good.
So, is that tabulated in the last one?
No, it's in the
It's in the text. Yeah. Sorry. So yeah, we actually were pretty stable. It was actually very impressive.
That's less than 1%.
Yep. So yeah, less than 1% variation. So the radiation. So what we could provide AMSAT for that specification, the 30 kiloreds radiation dose over the 5-year mission, was we could provide them with a level of assurance. We don't have a means of testing. AMSAT at some point will test the board. But so here's some of the tabulated data for the parts that we use that we could find test data from either NASA, NASA JPL, Ford Aerospace, and a few other companies. And when we found these documents that showed that the components could last the entire mission, we used those components. So yeah, and when we couldn't find data on parts that we needed, what we would do is we would look at the architecture of the part and make basically an educated estimate on the radiation tolerance. So is it CMOS? Are there boost?
Microcontrollers.
Yeah, are there microcontrollers or boost converters in it? Are there They're CMOS or BJTs. So yeah, as far as we can tell, we met that spec. All the parts on there, to the best of our knowledge, are sourced with that in mind. And the component height restriction, so our maximum was 8.1 millimeters. That's when you hit the top board. The ideal is 5 millimeters above the board. So that's the guaranteed spacing. So we aim for the 5. Overall, we did achieve that. With the design, we specified that none of the parts went above that. During bring up, we actually realized that since we needed more input and output capacitance than we had expected, what we can gather from that is that was due to the likely the open loop nature of the buck converter, as well as possibly some compensation issues during bring up that caused those values to increase greatly above what was calculated. We actually had to stack some capacitors to get the right amount of capacitance on there, which was not expected. So the board as it is goes to about 5.5 millimeters, but had we known that beforehand, we would have just placed them next to each other and it would have been fine. So yeah, that was during bring up, just trying to get to that level of capacitance. Yep, and here's the finished board. All the flight parts were constrained to the Fox 1 power supply unit board outline dimensions, and this circuit right here is one MPPT string completely constrained to 1/4 of the board, showing that we can fit 4 of them in a flight configuration. And here is a second MPPT string spread out over the half the board, just to make it easy to work with. And just to note, there's actually quite a few do not populate parts on here just for testing. So when you take those out, you actually get a bunch more space.
Okay, so going to the IHU communications, one of the specifications.
I need to leave.
Okay.
I want to congratulate you and you guys for an excellent work. I hope I will have you guys around for the next team like this.
Thank you.
Thank you.
Thank you.
Thank you very much.
I
And pre-work.
had basically zero contribution. Before I leave, one comment. You mentioned that you were also surprised by the amount of power that the solar cell would output.
Yes.
And there would be only a few changes, a few components that would need to be changed.
Mm-hmm. Possibly. We haven't done that would be due to NASA D-rating. Yeah.
Okay, well, if you can come up with a quick procedure or pointers in an appendix of one of your documents saying, well, if you're changing the solar panel and these are the changes that you have to make to the circuit of the board, I think that will be helpful not only for the next generation but also for the AMSAT guys.
Yeah, thank you. That's a great suggestion. I invite you to read this document. It's up on our edge. We'll send it out. But we actually go a little bit into that, what components would change.
Yeah.
So we'll specify more specifically, but you hit it right on the head. So.
By the way, just to note, you're actually on page 50 of 51, so you
almost
made it.
Yeah, but
Thank you for coming.
Thank you.
Thank you.
So, yeah.
So I guess moving on to the IHU communications, one of the specifications from AMSAT was that as a secondary mission, we report data back to the internal housekeeping unit, just solar panel temperatures, solar panel voltages, system current, etc., and in a pre-specified package structure. And everything worked as expected. The CRC calculated as expected. Brent wrote a Python script basically act as the IHU, using a little USB to serial, USB to I2C adapter to communicate with the board and between the board and his laptop. So he acted as the IHU.
So basically, I acted as the Fox 2 satellite.
Yep. So, so it would periodically request the data and then parse the packet, parse the packet as expected, and plot the data as you saw a little bit earlier, and display.
Just to go a little bit more in depth, I didn't put the graphs in here. I referenced the graphs throughout the document. All of the graphs that you saw from the temperature testing, and some of the other graphs that I mentioned in the document here were all taken from the MSP 430 on board the MPPT. So all of that's example data of what we got. And I also mentioned in here that we did duration testing
Oh,
So-
yeah. We actually ran this, I think, for 3 days.
3 days.
3 days straight, and both items still worked. Both items still worked. This kept requesting information as expected, and I kept the firmware on the board kept replying with relevant data as expected.
So, and I just excuse me, I've shown this simple Python interface. It's very simple. 3 buttons: quit, start, and stop. So very simple, and it starts logging data from the MPPT, and it logs all the data, shows you relevant data. And as you can see, we're pulling about 1.46 amps of system current. The X panel voltage was at 21 volt, just over 21 volts. So you can see live data from it.
Oh, and just as this was actually a concern, was that the CRC generation, since it's very computationally intense, it was actually a concern that it might take too long to compute the CRC, and then the data would have to be cached and automatically generated before it was requested, so always be a little out of date. But luckily that was not the case, and so all the data is basically sent on the fly. You know, they always get the most up-to-date recent ADC values. The CRC ended up taking just about, with the CRC, it took about 500 microseconds to respond. Most timeouts for I2C are kind of are about 2 milliseconds and above. Some of them going to about 18 milliseconds or 30 milliseconds, as some specifications state. So it's well within the allowed range. So it responds quick enough to not cause any issue.
And that pretty much wraps up our test document and the overview. Hopefully we showed you guys that the MPPT works, that it can be scaled, and that we've achieved all of our engineering specifications. I invite you all to read the actual document that we're presenting, along with the technical paper and all the theories of operations. They overview the design, overview the test results. We go really in depth into actually what the test results mean and how to
And
how to
actually why
analyze
they
them.
work. And
Why they work, why maybe some parameters change that we didn't expect. So I invite you to read that. And we can't demo the board right here because we need power supplies and everything else, but we could run downstairs if you guys would like. We also have a couple of videos on YouTube as well that show the operation outside, actually, with solar panels. So, are there any questions at all?
Very commendable job, by the way. You guys really paid a lot of attention to the details and really did a very thorough job. I think if I were starting a company, I would certainly want to have you 4 guys on the team. Absolutely.
Thank you.
Thank you.
Yeah.